Hi students, welcome back to the online video lectures on DSP. This is the second video lecture on sampling. Uh, in the last video lecture we have seen some basics of periodic sampling, and in this video lecture we would take a look at frequency domain representations of the sample signals. More specifically, we would be looking at what would be the relationships between the sampled version, the Fourier domain, that is DTFT of the sample signal versus the CTFT of the original continuous time signal. Okay, let's start. Okay, let me begin with the block diagram, giving you the block diagram, drawing the block diagram again, which we have did last time, but let me make it more complete in a way. So what you had is the original signal, continuous time signal xc of t. In order to obtain a sampled version but still a continuous time signal, it is multiplied with an impulse train. Okay, then there is this integral of nt minus epsilon to nt plus epsilon. Okay, and let me, instead of that, just for the sake of simplicity in writing, let me write it as analog to digital or discrete. Okay, so what you have here is xs of t, sample signal of the original continuous time signal. Here you have x of t, and assume, then again for the sake of completeness, I'll draw some blocks which you would be clear in the subsequent lectures only. Assume that there is an impulse generator here. If our goal is to again get back xc of t, yeah, by the way, this what you have here is a discrete time signal here, which is x of n. If you give it an impulse generator, or I would rather put it digital to analog for the sake of simplicity. Assume that this digital to analog would give you xs of t again, and then you have a block with impulse response hr of t. Assume that this is a reconstruction filter. Okay, this is a reconstruction filter. So since you have samples of your analog signal, that from those samples you want to construct the complete signal. Okay, we will come to those blocks in the subsequent classes. Okay, and this, the reconstructed signal, let's write it as xr of t. Ideally you want, this is just ideally you want it in a way that xr of t is equal to xc of t. Okay, some things which we already derived in the previous class, let me quickly note them down here. The impulse train which you give here is nothing but n varying from minus infinity to plus infinity delta of t minus nt, right? And here t is the sampling rate, omega s would give you the sampling frequency, and xs of t, the expression for it we have derived in the previous class, which is, we started with writing it as xc of t multiplied with s of t, and then making simplifications there using the shifting property, and we ended up with the expression that this is equivalent to n is varying from minus infinity to plus infinity. I could write it as xc of nt into delta of t minus nt. This is what we got. And of course, as we already know that x of n is nothing but xc of nt, I could have written this here as x of n as well. Okay, Thus, keeping in view of what we are going to do subsequently, I am writing it as x of n here. Okay. And another thing we derived in the last class is, if we know that this xc of t is a band limited signal, okay, this is the spectrum of xc of j omega. What would be the spectrum of this being omega n minus omega n, this being omega? We worked out what is the spectrum of xs of j omega, correct? It has a multiple copies of it placed, each copy placed at integer multiples of omega s. So that's k equal to minus infinity to plus infinity xc of j times omega minus k times omega s. We have also seen there omega s is nothing but 2 pi by t, the rate at which you are taking samples. This was the block diagram which we worked out in the last class itself. Okay, except that I added few more blocks there in order to reconstruct the signal. Right, this is the block diagram as of now. Let me now look at the relationship between, let me first, in this block diagram, let me first focus on this xs of t and x of n. And of course, the Fourier transform of this would be xs of j omega, right? And this being a discrete time signal, here the Fourier transform is discrete time Fourier transform, x of e power j omega. So what we will derive now is relationship between, is a first step or a second one here, we will derive relationship between xs of j omega and x of e power j omega. Okay, this is what we will do now. We have one way of defining xs of j omega just above this, but another way is, suppose if I know xs of t is given, okay, xs of t is given, so then this being a continuous time function, how could I write xs of j omega? This would be nothing but the CTFT, right? So xs of t, and then the CTFT of it would be xs of j omega. So let me write that definition of it. So varies from minus infinity to plus infinity. Xs of t, what would come here? Complex exponential minus j omega t dt, right? Do I know the value of xs of t? Yes, this we derived in the last class. We summation minus infinity to plus infinity x of n. So that let me substitute here. So this is equivalent to minus infinity to plus infinity summation over n varying from minus infinity to plus infinity x of n into delta of t minus nt, right? Delta of t minus nt. This is the expression for xs of t, anyway multiplied with e power minus j omega t dt. Okay, now pay attention here. Just a minute, this got closed, right? So pay attention here. This delta of t minus nt is non-zero, then only it has a value. That means this t has to be equivalent to nt, then only you have a value there. So only for those values of t for which this is equivalent to nt only, so this is non-zero, let me write it that way, otherwise this is non-zero, only when your t value is equal to nt. For all the rest of the values of, anyway, for all possible values, this n, t is a capital T is a constant, n is an integer multiple, so that is there within the summation. So I could simply get rid of this integral and substitute in place of t nt, correct? So doing that will give me n equals to minus infinity to plus infinity x of n, and non-zero, that means also this is equal to 1, and x of n into e power minus j omega, and this value is equal to t equal to nt. That's what I'm substituting here. So this is an important result again. So let me write the final result here. Xs of the CTFT of the signal obtained by multiplying the original continuous time signal with an impulse train is equivalent to, the Fourier transform of it is equivalent to n equal to minus infinity to plus infinity x of n into e power minus j, let me just club, omega t times n. Okay, that's an important result. Okay, now we already, suppose x of n we know, right? Already we know that the x of n is a discrete time signal. The DTFT of it is equivalent to x of e power j omega. Given x of n, I could write x of e power j omega as summation of n varying from minus infinity to plus infinity x of n into e power minus j omega n. Okay, this is just, we are substituting using the definition of x of e power j omega. Now you compare this expression 1 and expression 2, and you could notice here that, can you now express x of e power j omega in terms of xs of j omega? What is the difference there? In place of small omega, you have capital omega into t. So suppose if you compute its value at capital omega equals to omega by t, that means then x of e power j omega is nothing but xs of j omega is equal to x of e power j omega. In fact, I could also write it as xs of j times omega by t. This is the relationship we were looking at. This is what gives us the relationship between x of e power j omega and the Fourier CTFT of the resulting signal obtained after multiplying the original signal with an impulse train. Hope this is clear. It should also make sense to you here, because look, in this signal xs of, I think something got messed up here. This is analog to digital. See, the only difference between xs of t and x of n would be in its axis, roughly, ignoring the span of infinitesimally spread of the delta continuous time delta function. You have the values at 0, t, 2t, 3t, and similarly on the negative axis as well. Whereas when it comes to xn, what happened to the axis? Instead of having 0t, 2t, 3t, you have now 0, 1, 2, 3, 4. The time information is not there, isn't it? So if you keep that time information, so that's essentially scaling it by a value of t. If you scale it, that's what you would be getting here to x of e power j omega. So exactly that's what is happening here. Now x of e power j omega is equal to xs of j times omega by t. Okay, yeah. Now the next thing is, now we know the relationship between, can we now, given that, see here, this is giving us the relationship between x of e power j omega and xs of j omega. We already know how xs of j omega is related to xc of j omega. By the way, I have forgotten here, if you remember, there is a normalizing factor of 1 by t also would come from the previous lecture. So let me keep 1 by t here also. Okay, this is the relation. So can we not now establish the relation between the CTFT of xc of t and the DTFT of x of n? Okay, that's what we will do now. So the third part now we are going to do now is relationship between xc of j omega and x of e power j omega. That's what we will do now, right? Yes, I am just rewriting the earlier one. We already know that xs of j omega is equivalent to xs of j omega is equivalent to 1 by t times k varying from minus infinity to plus infinity xc of j times omega minus k times omega s. I could have also written in its place 2 pi by t, right? So this 1 2 3 1 2, there is one more bracket here. Okay, this is the relation, we already have it. Now from the above section, we already had x of e power j omega is nothing but, so in place of that is nothing but xs of j omega computed at omega equal to omega by t, right? So that implies you could now establish the relationship between x of e power j omega as nothing but 1 by t times k varying from minus infinity to plus infinity xc of j times, in place of omega you have now omega by t minus k times 2 pi by t. That's all. We have now the expression of x of e power j omega in terms of the CTFT of original continuous time signal. Okay, right. This is also, again, notice here what's happening. You had initially, let's try to again summarize the things. Suppose this is the Fourier what is happening to the frequency spectrum. You have a continuous time signal, you multiply it with an impulse train. So in the frequency domain, it's equivalent to convolving with an impulse train. So you have multiple copies of it placed. Along with convolution there, multiple copies placed there. This convolution would also introduce 2 pi by t. That 2 pi anyway gets cancelled there, and there is a scaling factor of 1 by t to the magnitude, followed by placement of these multiple copies of it are placed at each omega s there. Okay, then the moment you are converting it again to the time domain, additional thing that would happen now is this excess of j omega will also get scaled along the omega axis, and the scaling factor can be given by capital omega into t. Capital T is equal to small omega. So this is the capital omega into t is equal to small omega. That's what the relationship. So omega axis now is equivalent to omega times t. Okay, these are the relationships, two important relationships. So if you now directly combine both and now try to interpret x of n spectrum with respect to the spectrum of xc of t, you could say now that you will have multiple copies of it placed, okay, and that placing is equivalent to is placed at capital omega times t, okay, that is where each copy is placed, and its magnitude is scaled by a factor of 1 by t. That's how you could interpret this final equation that gives you the relationship between xc of j omega and x of e power j omega. Okay, now one more, let's plot these graphs. Okay, so what we do now is you take a summary of it in terms of the plots. Let's start with when there is no aliasing. Let's start plotting that. Okay, assume that, yeah, whatever we have discussed now orally, we'll do the same thing here. You have assumed that you have a signal. This is the magnitude plot of xc of j omega. Okay, the original discrete continuous time signal. This is omega. Assume that this is your omega n. This is your minus omega n. Okay, this is your y-axis here. Assume that this magnitude is equal to 1. So what happened, which we have drawn in the last class as well, when we move from here to xs magnitude of xs of j omega, what has happened? So your y-axis is omega. This would get scaled. Okay, this will be still this omega n and minus omega n when there is no aliasing. Okay, another copy, so this magnitude will become 1 by t. This gets placed at omega s now, depending on your t value. Assume that t is good enough to avoid any aliasing. You have then these copies placed at omega s, 2 omega s, and so on. Okay, similarly on the negative side, this is omega s. Assume this is minus omega s. Is all assume, yeah, I should be having all same magnitudes there. Okay, this 1 by t, and this distance is also same, minus 2 omega s, and one more here, minus, let me switch off, let me mute the sound. Okay, this is minus 3 omega s, and so on. This is as far as xs of j omega is concerned. So in this class we have went ahead one more step. We have gone one more step ahead, and where did we end up? Now we move to omega here, right? With respect to this, all that has happened is a scaling, where omega times capital T is your omega. Okay, earlier a copy is placed at omega s. Okay, so let's write here, when omega equals to omega s, which is equal to 2 pi by t, then the corresponding small omega would be equivalent to, which is originally omega times t, is equivalent to 2 pi by t times this t, which is equal to 2 pi. So the copy would be now placed at a value of 2 pi. Okay, this whole thing got scaled. That scaling is simply by a factor of t. Okay, so now, yeah, this for example is equivalent to now omega n times t, and this is minus omega n times t. This 2 pi will be a bit far than what it is shown here. Let me draw this out again. Okay, so this and copies of it are placed this side as well, but now this will be 2 pi and this is 4 pi. Okay, by the same logic, this is minus 2 pi These are all, I assume that those are all identical triangles there. Okay, the same. And this, anyway, this magnitude in the y-axis, there is no difference, right? This is what you could see from the relationship here. X of e power j omega and xs of e power j omega, there is just the scaling happening. So that's all. If you do it, you got this thing, right? And also, of course, you could this is magnitude of x of e power j omega. Right. One more thing, you already know that this is periodic. DTFT is periodic with the periodicity of 2 pi all the time. So that property also you could see coming again from multiplication with t. Okay. So one more graph, let me draw it here, where I do things now when there is some aliasing. Okay. So this is the last part of it. Summary when with aliasing. That's what, let me do that out. The fifth. Let me draw summary with aliasing. Right, let me quickly draw all those things again. You have, this is omega, magnitude of xc of j omega. Okay, this is your y-axis. Assume that this value is 1, magnitude of xc of e power j omega. Your t is very large, or omega s is less, in other words. In that case, what would happen when you come to xs of j omega? This omega s is much closer here, so that would give you an overlap here. So the copies are placed with a overlap. This is magnitude is equal to 1 by t. Okay, now this is your omega s, 2 omega s, and so on. 0 minus omega s minus 2 omega s. This is omega. This is magnitude of xs of j omega. Next step, you are going to draw for x of e power j omega. That line has come too badly. Somewhat better. Okay, now this would remain same. The height would remain same, 1 by t, except that there is a scaling that is happening along x-axis. So with that scaling uniformly across this omega axis, you would still end up with the same proportion of overlap here. So this is, for example, your 0, 2 pi. Okay, if you want, this value would be equal to omega n times t. Okay, so then this is 4 pi and so on here. This is minus 2 pi, and let me draw one more for the sake of completion, and this would be equal to minus 4 pi, and the same thing continues here, and that would give you x of e power j omega. Okay, that's all for now. I hope this is clear. Let me now, with this, let me go back to the original mode. Right, so that's all we have discussed. To summarize, we have discussed the frequency domain relationships between xs of j omega and the x of e power j omega, followed by this xc of e power j omega and also x of e power j omega. These are all we discussed, and we have drawn how the frequency magnitude spectrum of these frequencies would look like when there is aliasing and when there is no aliasing. The rest of the things we will continue in the next video lecture. Hope things are clear. If there are any questions, you may post them in the YouTube in the comments, or else you could also discuss in our next conference call. Yeah, thanks for watching. and see you in the next video.